So as we move into factoring general trinomials, remember these are just basically ordinary trinomials. So there's nothing special about them. So recall if I gave you x plus say 3 times say x plus 4. This is the factored form. And if you notice, if I multiply this out, this is going to be x squared. So the first terms, if you will. Let me do that a little bit cleaner. Sorry with that. Try that again. So I'm going to multiply the x through using FOIL. So x times x is going to be x squared. And then x times 4 would be 4x. And then if I bring the 3 through, 3 times x is 3x. And 3 times 4 is 12. So notice how if we do it this way, we end up with x squared plus, sorry again, getting ahead of myself there. So x squared plus 7x plus, I didn't get that right, did I? What is 3 times 4? So 3 times x is 3x. 3 times 4 is actually 12, isn't it? Y'all caught that, didn't you? So x squared plus 7x plus 12 would be our solution. Now, I can also organize this as a box, if you will. We call this find the area, because area represents, you multiply the edges. So the edges become the factors. So notice that I could put an x and a 3 here, and an x and a 4 here. So instead of using FOIL, I have what's called the box, or Foursquare, if you will. So if I multiply the x through these top edges here, x times x is going to give me this x squared. X times 4, or 4 times x would be 4x, if you will. So a lot of times I like to go x times x is x squared, 4 times x is 4x. And then x times 3 would be 3x, and then 4 times 3 would be 12. So notice that if you do the box, though, the like terms, the middle terms are actually diagonal of each other. So what we have then is x squared is the first term, and then the 3x and the 4x gives me the 7x, and then there's this 12. So there's two ways of doing it. We have what's called the FOIL, and we have what's called the box. Now, the thing is, when the coefficient of x squared is 1, this actually becomes very easy. Notice that the factors of the last term, the c, must add up to equal the linear term coefficient, which is the b. So if I look at the expression x squared plus 7x plus 12, if I look at the factors of 12, if you will, the factors of the constant, again, I can make the factors of the constant using the calculator. So to create a factor table, if you will, I can go y equals, I can clear this x squared out and just put 12 divided by x, if you will. So the 12 is going to be divided by x. Now, if I go to my table, notice that 1 times 12 is a factor pair. 2 times 6 is a factor pair. 3 times 4 is a factor pair. And then we get 4 times 3 is a factor pair. But notice that 4 times 3 is the same thing as 3 times 4, so that just tells me. So notice how we have 3 different factor pairs. So these are the factors of the constant, 1 and 12, 2 and 6, 3 and 4. But the catch is they must add equal the linear term coefficients. So they must add up to equal the 7. So they have to add up to equal the 7. So 1 plus 12 does not equal 7. 2 plus 6 doesn't equal 7. But also 3 plus 4 does equal 7. So that's my winner, if you will. This is my winner, the 3 and the 4. So what I do is to factor this, the x squared, so what I do is I set up two sets of parentheses, And the x squared just takes up the first two positions because that's where the x squared comes from, is x times x. There's no option there. But what I put here and here are actually just the factors of the last term. So the 3 and the 4. So the 3 and the 4 would come into play. So notice that x plus 3, x plus 4 becomes the factored form. And notice how we started out with x plus 3 times x plus 4, and it did turn into x squared plus 7x plus 12. So we're trying to reverse this process. So if I want to do this problem right here, notice how the coefficient is 1 in front of the quadratic term. So again, the quadratic term is the x squared term, if you will. It's the power of 2 term. So quadratic term is what's called degree 2. Degree 2 means the exponent of the variable is a 2. So the coefficient is the number in front of the x squared. It's a 1. So if we have a general trinomial that takes on this form right here, x squared plus bx plus c, if the quadratic term has a coefficient of 1, then all we really got to do is focus on the factors of the constant that up to the factors of the linear coefficient. So what I'm doing is focusing on the factors of 60, but the factors of 60 must add up to 23. So the way I do this, a lot of times, is I'll make a table if I can't do it in my head. So I'll write down my 60, and I have to get this 23. So to get my factors of 60, I can use a calculator. So I have them go y equals, and then clear this off and go 60 divided by x, if you will, and go to my table. And that's how we did get 1 times 60 is 60. 2 times 30 is 60. 2 times 30 is 60. Is 3 a factor of 60? Yeah. 3 times 20 is 60. Is 4 a factor of 60? 4 and 15. Is 5 a factor of 60? 5 and 12. So anyway, it's a lot of factors for 60. 5 and 12. 6 and 10. And then it looks like 10 and 6. But notice how 10 and 6 is repeating. So what I have are 1, 2, 3, 4, 5, 6 factor pairs. But what I'm looking for is the factor pair that actually gives me a 23. So what I'm seeing then is 3 and 20. Those are the factors of 60, but they do add up to the 23. So if the coefficient of the x squared is 1, all I got to do is focus on the factors of the 60. But the catch is they have to add up to the linear coefficient, which is that 23, or in other words, the b. So the factors of the c must add up to the b. So what I can do is I can set up two sets of parentheses here. The only way you get the x squared is the x times x. And then what I put here are the factors of the last term, the 3 and the 20. So the 3 and the 20. And it doesn't matter what order you put those in. You could put the 20 and 3 together as well. So that would be the factorization of a general trinomial, is we kind of use this strategy.